Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we are going to discuss the stack data structure. Stacks are a linear, high-level data structure that we use to model occurrences in real life and in our software where we care about the last item and operating on things that most recently happened. But before we dive into the theory, let's really go through how a stack stores its data. You can think of a stack maybe like a pile of dishes. As you use a dish and add it to this pile, you continue to add one on top of the other, where the oldest is at the bottom and the most recent is always at the top. Then, when you go to clean the items, you grab the item off the top, clean it, and then work your way down. So you grab that last item added, or the most recent item, and then you clean until you reach the bottom, which is the oldest. Another common example is your browser's history. As you visit websites, it stores those sites in a stack. So you go to Google, then you go to getconnected.com, and then you go to skilled.dev. So it stores all these sites in order, and then you reach the most recent, but then when you hit the back button, you start removing them off the top of the stack. So you go from skilled dev to get connected back to google.com. So when we have this functionality where we use the most recent item or the last item, it's called last in, first out, or LIFO. And this is really the fundamental concept of a stack. You're always using that last item added. So now let's visualize a stack and how we might think about it in our code. We're going to push items to this stack where they have a string. And the first one is going to be bottom. So we push bottom to the stack, then on top of that we push middle, and on top of that we push top. But then when we use the stack or remove items, we take the top item. So we pop off each one until we reach the oldest. So I said stacks are a high-level data structure. They're high-level because we actually implement them using other data structures. Most commonly, we use a linked list or an array. You can think of a dynamic array where you push items to the end and then pop them off the end. And this is exactly how a stack works. And also with a linked list, all you need is a pointer at that last item. Then you can get these very fast constant time push and pop operations because all you need to do is update a pointer to change the reference when you add or remove items. And you can actually see how to implement a stack further in the course. Stacks are also linear. So they're ordered from the most recent item to the oldest item. And you may be wondering, well, why do we treat stacks this way? Why do we have this limited functionality when we use something like an array? And this is very intentional because with a stack, we want the purpose of using a stack to be very clear. It really needs to indicate what we're trying to model. But also, by limiting the functionality, we can really optimize around the operations we care about, which is fast operations on that last item. And we can see that here in our big O complexity. We can add an item or push it to the end in constant time. We can remove an item or pop it from the end in constant time. And we can peek or view that last item also in constant time. And the data structure itself is O of n linear space because it just stores n items. So as we can see, the fundamental part of a stack is optimizing around these fast operations at the end. So now let's go through the pros and cons of a stack and why we might want to use one. The main pro is we get fast access at the last item. As we've already discussed, this is the fundamental concept of a stack. So you can add, remove, or access the last item in constant time. So specifically, we're going to use this when we want to model things where the most recent item is the most important. For example, a browser history. And also, a stack is ordered, newest item to the oldest item. That's why it's also a linear data structure, similar to maybe a queue or an array or a linked list. There's this clear path from the beginning to the end. The downside to a stack is it has slow lookups. Because you can only access items at the end, if you want to find any item in the stack, you need to pop off each item until you locate it. So this can be a worst case O of n linear time. So if you ever need to access items that aren't at the end, a stack is not going to be a good choice for your data structure. So stacks are actually very fundamental to computer science. You've probably heard of the call stack, and this is what most languages are based on. When you execute code and you execute functions, you're going to add these items to the call stack every time you execute a new piece of code. So here, we run the function 1 with the ID 1. It becomes the first item in the stack. So we look at the run function, it takes an ID, but then it calls the calculate price function. So run can't return until we execute calculate price. We pass price a new item. So both of these are added to our call stack. Then to calculate the price, well, we can't return until we also calculate the tax. So we add another item to the call stack. Then we calculate our price. And once we have this, we're done with our function calls. So we can start to pop these items off the stack, return the value, and then finally run the entire code. As you move down, you eventually reach the beginning and get your final answer. But the thing about the call stack is it actually takes space in memory. Every time you add a function to the call stack, the computer must remember what it does and what items it's waiting on. So this also means there's a limited number of functions you can add because our computers have limited memory. So let's say we start calling functions, and each of these functions call another function, so it must wait for those to pop off before it can also be removed. Well, now we've reached the top of our memory. We have no more space. So what happens if we add another function, or we call another function within our code? There's no room. And this is what's called a stack overflow, when your stack runs out of memory and your code can no longer continue to execute. And this is bad. This means your code is going to blow up and cannot produce the answer you're looking for. This is most often seen in recursion, where you continue to call the same function over and over, and you incur this space on the stack as big O space, but then you also have the risk of using too much of the memory and not being able to finish executing the code, causing your program to crash. So stacks appear pretty frequently. For example, you can think about when you work in your text editor. If you make a mistake, you might hit Command Z, and this undoes the most recent thing you typed. And what's happening is the text editor is storing versions of this file on the stack. So each time you make updates, it's a new item on the stack, and when you hit undo, it removes the most recent item and moves you to one before. And if you continue to undo, you'll pop items off the stack until you reach the beginning of that file. We've already discussed it, but a browser is a very common example. And as you add websites, it's the same as our text editor. You build up the stack, and then when you hit back, you pop the items off, moving backward in time through the websites that you visited. When we receive emails or look at messages, those items are in a stack. You usually are given the most recent first and then must work backwards to find the older items. This one may not make sense until you go through the tree and graph section, but depth first search is fundamentally built on a stack. And that can be the call stack or a stack data structure that you implement yourself. In interviews, you can see stacks in a few different ways. One of the most common is when you're trying to find balance, because when you balance brackets or balance parentheses, you stack items and then you check the other side if it has a match using this stack. Another common example is a minimum or maximum stack. When you have data coming through, if you want to know what the minimum or maximum is, you store these values in a stack, and then as those items leave, you pop them off the stack. And finally, queues and stacks are very much related. They're very similar data structures, and you can actually implement a queue with a stack, and this is a common interview question as well. And that's our introduction to the stack data structure. So now we can dive in and start answering these interview questions based around stacks.